So chapter 12 starts today, and this is our last chapter. We covered half our book, you guys. Chapter 12 is about solids, okay? Um, we have two different kinds of solids. We have metals, which make up metallic solids. They're kind of different in the sense that they have a different type of bonding, which we didn't talk about a lot. We talked about ionic and we talked about covalent, but um, with a metallic, solid, the electrons can just move everywhere. They have no bounds, okay? Ionic, they have, you have your ions. There, this is a strong bond, and covalent isn't as strong because they're not held together as much, okay? So a metallic solid, you have the sea of electrons, that's why they're good conductors and so on. Ionic solids, remember we have cations and anions, positive and negative, attracted to each other. And then we have the covalent network solids. They have a bunch of covalent bonds attracted in the molecule itself and in between the molecules, okay? And then they have molecular solids. These guys have very, very, very weak forces, okay? So we have different types of solids, okay? The other two types, there's a polymer. A polymer is a long chain of atoms. They're connected with covalent bonds, but they're chains. They're very long, and their bonds are going to be very, very, very weak, okay? And then there's nano. I don't know if you've heard about nanomaterials. It's a big thing in chemistry right now. They're using nanomaterials. They're super, super, super tiny, obviously. And what they do is they add them to other structures to give them strength. Okay, it changes the properties by adding these little tiny materials. Okay. When you talk about solids, we've always talked about solids as having definite volume and definite shape. Okay, like here's pyrite, which is an iron sulfate thing. It has a definite shape. They're hard to melt. They have high boiling points and all that. We also have amorphous, and amorphous is they can actually change their shape, like wax. Glass is considered amorphous. Glass actually flows. If you've ever made like slime, or one called GAC, where you make it out of corn starch and water, it's a solid, but it can change it flows. It can change its shape. So they're different. And again, these are much weaker bonds. Okay. So crystalline solids have very regular patterns. Those are the ones that people deal with more. The amorphous ones, since you can't figure out their pattern, you can play with them. They're really fun to play with. Okay, so when you're looking at a solid, they have a repeating pattern called a unit cell. So the structure of a crystalline solid is defined by the size and the shape of the unit cell, where the atoms are within the unit cell, and then they make a pattern. Okay, it's called the crystal lattice. If you look at salt crystals, okay, salt would be an example of a crystalline solid. All the little crystals are the same. They have the same crystal lattice pattern because of the ions being attracted in the same pattern always, okay? So if you have a crystalline solid, they have a crystal lattice, which is the geometric pattern that they form, and it's always the same, okay? They have points in the overall structure. They're called lattice points, and what they are is areas where they join up. Okay, each lattice point is identical. All right, so again, when you have a crystalline solid, you have a crystal lattice with these little points, and they're always the same. Okay, they also have vectors that connect the points. So again, the thing to remember about a solid, if it's a crystalline solid, it has the same shape because it has this crystal lattice. Okay, and here's some different patterns that there's two-dimensional lattices, and there's three-dimensional lattices, okay? And again, they're all the same. I don't expect you to memorize these. I just wanted to show you some of them, okay? If they're primitive, they only have a few lattice points. If, again, they're centered lattices when they're in the middle, would be a centered one. They have a body center and they have a face center. And again, I'm just showing you these. You don't really have to know them, I guess. So if you have a metallic structure, now these are made out of metals, remember, here's your atom of your metal, and then they form like you can see, they're not really a cube, but when you put the metal atoms in there, it looks, you can put a cube in there. So this is a primitive, this is a body centered, this is a face centered, and these ones are called, you can't read it, it says corner atoms, they're 8 unit cells stuck together. So you take a bunch of these and put them together. Okay, so not every part of the atom on the lattice is completely within the unit. Some of them stick out, like you could see here. Okay, if this is the unit, you can see how these guys are sticking out. Again, because they're round. Okay, so that's why you end up with not every point is on there. Again, in a unit cell, you can determine how many atoms are in there. If it's like here, there's got to be 8. They meet at the corner. Okay, so therefore, only an eighth of the corner atom is within the meeting cell. The rest of them are stuck out. Again, if there's 2 cubes, half of it is out. And again, it's because you got round atoms, and they make the structure square. Okay, they're very closely packed in. You can see that. Nature does not like empty space. Nature likes to squeeze these guys as tight as possible. So the atoms are going to be in a crystal, and they're going to be packed as close as they can. Okay, and there's 2 common types of packing. One is called cubic close packed, and the other is hexagonal. You can see here's the hexagonal down. Oh, here's the side view. Sorry, here's a side view of the cubic, and here's the hexagonal. Okay, and again, they just get packed in layers, layers upon layers upon layers upon layers. So when you see a little crystal, there's a bunch of atoms in there, but again, atoms are too small to see. Okay. One of the important things that we make out of metals is alloys. Okay, an alloy is a mixture of metals. They're mixed really, really well, but what happens is, we have metal characteristics that we really like, but by themselves they don't do well. Okay, so here's some examples of alloys down here. We have wood metals, we have brass. Brass is very common, which is copper and zinc. We have bronze, which is copper and zinc, or copper and tin, excuse me, in different forms. Stainless steel is a huge one. They used to build a lot of things out of iron, but iron rusts. It rusts a lot. So they started adding carbon, chromium, and nickel to it. And now we have stainless steel, and it doesn't rust. Okay, some people think steel is an element. No, it's mostly iron, 80%, but you add these other things to it. They coat it, and then you don't get that rust. Okay, there's solder, which is lead and tin. Sterling silver, because regular silver rusts. If your grandparents might have sterling silver, like silverware and stuff, and you have to polish them, silver will form a tarnish on them. But if you have sterling silver, it won't. And it's silver and copper. Okay, the stuff they put in your mouth: silver, tin, copper, and mercury. Okay, and pewter is mostly tin, but it also has antimony and copper in it. So these are alloys. They're mixed together. Alloys are really common in jewelry. Okay, if you have a gold ring, it's not 24 karat gold. That's pure gold, because gold is soft. So if you get a jewelry made and it's pure gold, it's not going to last. So they add other things to it so that it's tougher, that it lasts longer. That's why you have 14 karat gold and 18 karat gold. Those are golds with mixtures. Okay, and it's important. The mixtures help make them better, last longer, resist corrosion, things like that. Okay, here's some types of alloys. There's a substitute and alloy where the second element takes the place of a metal. These would be examples. Okay, here's 14 karat gold, like I was saying. Okay, let's throw in a few little silvers in there. Okay, here's steel. You got to put copper. You got iron and carbon, excuse me, in there. And then they end up taking over they take over some of the metals. And then you also have ones that fill the space. Okay, so here's a substitute where they actually kick out an atom and takes its place. Here's one where they fill in the spaces. That's interstitial. Okay, those are a couple different ways of alloys. Because remember, alloy is a mixture. It is not, they don't combine chemically. Okay, here's another with the iron and the copper. You can kind of see where they're going. It's kind of hard to tell. But anyway, this is substitute like 14 karat gold, which is most what your jewelry is made out of. They take over. The silver kicks out a few gold atoms and takes its place. And then here is where it fills in the space with carbon. And there's also, remember, there's heterogeneous. These are homogeneous. When you look at 14 karat gold, it looks the same. Okay, so these are homogeneous. But there's heterogeneous where they're not uniform. Okay, and again, remember, these guys are not compounds. They're mixtures. Okay, they're not chemically combined. Okay, so you can mix them in any amount that you want. They might, sometimes they'll mix, sometimes they won't. But the ones that have been made have been, it's been a process where they've learned what works the best. Okay. Okay. They are ordered. They're not randomly distributed. Here you can see there's nickel and aluminum. Niobidium, I don't even know. I've never used niobidium, you guys. But anyway, they fill in. But again, these are compounds. These are not, they're called intermetallic compounds, but they're not really compounds. They're mixtures. Okay, you can add as much nickel to this aluminum as you want. It doesn't have to be any in 3 to, this is probably the formula that worked best, okay? And most of the time they're very brittle, which is weird for a metal, okay? All right, a metallic bonding, again, remember, we didn't talk about metallic bonding a lot, but what happens is when they get together, they just let their electrons go wherever they want. It's not like with an ionic compound where you transfer electrons, or covalent where they share them and they're found in a certain area, like an orbital. These guys just cruise all over. And that's why metals are such great conductors. They allow the electrons to go over, so things flow right through metals. Okay, they call that the electron sea. And again, that's why they're great at conducting electricity. They're great at conducting heat. Their characteristics, like you can stretch them into wires and you can hammer them to sheets, is because of these guys just allow them to do that. They move all over. They're not restricted. Okay, so an ionic solid, and again, this is made out of ionic bonds. You have the cations and the anions, and we've talked about those already. They have very, very high melting points and boiling points. They're very strong bonds. Okay, they're really tough. All right. Because the charge is centered on the anions, which would be the negative, they're electronic insulators if you put them in the right order. Okay. Oops, sorry. So again, ionic solids are very, very tough bonds, very strong bonds because of that attraction. Okay. The most favorable structures for the cation anion is so they're close together, but you don't want the anions to be close together and you don't want the cations to be. So they're going to situate themselves so the positive and negative are as close as positive, but the negatives are as far apart as possible and the positives are far apart because, the opposites attract, the other ones repel each other. So they try to move apart, okay? The 3 common structures are like salts, where it's 1-to-1. Here's cesium chloride. So, and then there's also where you get rock structures, like sodium chloride, rock salt, which we talk about all the time, and zinc sulfide. These would be examples of 1-to-1s. Okay, if you get the effect of the ion size, again, chlorine and sodium are smaller, zinc and sulfur are going to be larger, so you get different, structures because of their size. And again, it's because the positives are trying to get away from each other, and so are the negatives, but the positive and negative want to be close to each other, so you can see they form different structures. Okay, they call it the coordination, and again, it's based on the number in the structure. Not all ionic compounds are a 1-to-1 ratio. If you have lithium and oxygen, you're going to have 2 lithium for 1 oxygen, so you're going to have a different ratio. What do they have them down here? Here's NF, here's MgF2, okay? And they have the different shapes down here we talked about with VSEPR, the different shapes. Okay, so since other combinations exist, you got other structures, okay? And again, the coordination varies to give the expected ratio of ions based on, again, NF, that's 1-to-1. MgF2, that's 2-to-1. Here we have scandium fluoride, which is 3-to-1. So you're going to get different shapes because of the ions, okay? If it's a molecular solid, it consists of atoms or molecules. They might have a much weaker bond. They have in-between bonds, the dispersion bonds, London dispersion, and dipole and hydrogen bonds. Those are not in the compound. Those are in between, okay? And these are mostly organic compounds. This is graphite, which is like the stuff you're writing with if you have a pencil. Okay, the shape, the ability to stack changes their physical properties, like their boiling point, their melting points, what they look like, and so on. I think we can get, okay, and again, graphite is an example. Graphite is what you write with. If this got put under more pressure, it'd be a diamond, okay? And I think we're done, so that's it for this one.